Hello students, in the unit 3 we will have a discussion of the topic talk on the closed circuit. By definition, the force due to the current element we have already learned to be F is equal to I of L cross of B. For lever arm R, which is extending from the origin O to a point P where the force is being applied, the torque is defined by T is equal to R cross F. So it is defined as a tangential force times the radial distance at which it acts, or it is defined as a mechanical moment of force. Now consider 2 points P1 and P2 with forces of F1 and F2 such that the torque is defined with respect to the origin as T is equal to R1 cross F1 plus R2 cross F2. But by definition we know that F1 and F2 are in the opposite direction, so it is R1 cross F1 minus of R2 cross F1. So it is R1 minus of R2 cross F1, or written as R21 cross F1. Now let us consider the differential closed current loop in the magnetic field B to prove the torque condition of T is equal to M cross of B. For which case we are defining this analysis. This is the current loop, closed loop. It is defined with the sides of 1, 2, 3 and 4. Now the differential force is defined by force equation. F is equal to I of L cross of B modified as dF is equal to I dL cross B. This is one set of equation. Now from this only we are going to derive with respect to 1, 2, 3, 4 sides. I can rewrite the equation as dF1, dF2, dF3, dF4 such that the current passing through the element is I. So for side 1 it is dx of Ax vector is a line element. So I dx of Ax vector cross B. dF2 I dy, this is dy, so dy of Ay vector cross B. dF3, current is moving in the opposite direction, so minus of I dx Ax cross B, and dF4 again it is in the opposite direction, so minus of I dy of Ay cross B. This is one set of equation for differential force. Second set of equation we derive from torque equation. We know T is equal to R cross F, so differential torque can be defined by R cross dF. So let me define dt1, dt2, dt3, dt4 with respect to the four sides as R1 cross df1, R2 cross df2, R3 cross df3 and R4 cross df4 with respect to the four sides. This is second set of equation. Third set of equation in the diagram is very clear. I have a radius of, this is negative half region, this is positive half region. You imagine quadrature point also you can imagine. This radius is with respect to y. So R1 is defined with respect to side 1, it is R1, which is half the value of y in the negative point. So minus of half dy of Ay. R2 I am defining, which is positive of dx. This whole value is dx, one half of it is half dx. So it is in the positive analysis. Likewise I am writing R3 and R4, from which I can identify R1 and R3 are opposite. This is R1 means this is R3, this is R2 means this is R4. So only the sign differs. Now I need to find out the torque. So dt1 equation you take R1 cross df1. Substitute the value of R1 minus half dy of Ay cross, what is df1? I dx of Ax cross B. B is nothing but equal to bx of Ax vector plus by of Ay vector plus bz of Az vector. Now let me do the cross product analysis, for which I have taught this in the previous unit itself, in the first unit basics itself. The cross product of like vectors is equal to 0. Ax cross Ax or Ay cross Ay, Az cross Az is equal to 0. If it is in the clockwise direction it is positive. If it is in the anti-clockwise direction it is a negative vector. So Ax cross Ay is Az vector. Ay cross Az is Ax vector. Az cross Ax is Ay vector. So let me start substituting. Minus half dy of Ay is with respect to bx of Ax, with respect to by of Ay, bz of Az. Expand this. Now Ax cross Ax is equal to 0. First term is vanished. Ax cross Ay is equal to Az. Whereas X cross Az is nothing but equal to Ax cross Az you need to find out. So it is minus of Ay. Ax cross Az is equal to minus of Ay. That's what I have substituted here. So this is the value of I dx Ax cross B. First term I have identified. Now I have to again cross product it with respect to R1. So dt1 becomes equal to minus of half dy of Ay as such, right? Substitute the value which we have got for I dx of Ax cross B. Again do the cross product analysis. Ay cross Ay vector is 0. Second term vanishes out. You are left out with the equation of minus half dy I dx by. Ay cross Az is nothing but equal to minus Ax. Name this equation number 4. Similarly, I can write dt3 because dt1 and dt3 are same. Because df1 and df3 are same only with a negative sign, which is also modified in r value. So the value of dt1 and dt3 are same, minus half I dx dy of by Ax vector. Now similarly I can find out dt2 and dt4. dt2 just a modification. In dt1 I had by of Ax, here I have bx of Ay. That's a simple difference. Similarly I can write dt4 equal to, name the equations as 6 and 7. Find the total torque dt, which is equal to the sum of dt1, dt2, dt3 and dt4. So try to take the common terms. These two are common terms and these two are common terms. Add together. So minus 1 plus 1 when it is added up with. Take out the common terms. I dx dy of bx ay vector minus by of Ax vector. How can I rewrite this bx of ay minus by of Ax in cross product? If you do the cross product of Az cross B and check out, you will get bx of ay minus by of Ax. Because Az is 0, 0, 1. In the place of B, I have substituted bx, by, bz. Expanded, you will get this equation. So I am replacing this term by Az cross B. But dx dy is surface area, so I ds of Az cross B. But by definition, we know dm is a differential magnetic dipole moment, which is defined by dm is equal to I ds of Az vector. So the equation for dt is reduced as dm cross b, which in turn is defined by t is equal to m cross b, is the equation of the torque. Thank you.